Bismillahirrahmanirrahim. In this video we will cover the topic pulse code modulation, and the course title is EEE 351-352 Analog/Principles of Communication System. I am Dr. Zishan Kareem from EC Department CUI Campus. In this video we will cover pulse code modulation and non-uniform quantization. What is the benefit of using non-uniform quantization and why we need this non-uniform quantization? Okay, let's begin the lecture contents in detail. So, pulse code modulation is used as a tool to convert analog signal to digital signal. So, this is a complete block diagram that which shows the complete procedure of converting from analog to digital signal. So, this is the low pass filter, which usually used to limit the high frequency signals from the massive signal. So, after passing this, we pass to the sampler. So the sampler will convert the digital analog signal into the samples, and after passing to the quantizer will quantize or give the labels or the levels to the uh, sample signal, and after quantization we will pass to the bit encoder. The function of the bit encoder is to convert these levels into bits form. So finally we will get some digital signal like this 1011. So this is, for example, a signal, analog signal, and we are going to sample this one. So these are the samples. The black solid lines are the samples taken from this signal, and the sampling frequency should be greater or equal to twice of a bandwidth or the twice of a maximum frequency signal, right? So after taking samples, we need to quantize. So for example, this is the maximum peak value MP positive side and the negative side minus MP peak value, right? So this signal lies in between this range, right? So we need to divide this into the equal number of intervals from MP to minus MP. We need to divide this into intervals, right? So signal range is minus MP to MP is divided into L sub intervals. So there are L number of intervals, for example, 1, 0 to 0 to L minus 1, right, or 1 to L, right. So there are L number of intervals, this first interval, second interval, third interval, write this one into L number of intervals. And the size of each interval is this one, right. This is one interval, right. So the total size is this and this. So total size could be, because MP, how to calculate MP minus MP, right? It becomes MP minus MP over L, because there are total L intervals, so the size of each interval will become 2 MP over L, right? This is the way to calculate the size of each interval, and we represent that interval size with delta V, right? Delta V. So delta V is the interval size, and the size of the each interval is 2 MP over L, right? And L level requires n binary digits. So if we have a L number of levels, so to represent these levels we require n bits, right? For example, 2 raised to power 3 we have a 8 levels, right? 2 raised to power 4 we have a 16 levels, right? So bits and the levels are interdependent. So to these L are usually called the quantization levels, right? So if you have a more number of levels, then you have a more accuracy. This should be remembered. So because if you have a more number of levels, you will transmit more number of bits to represent each level. So in this way, your accuracy will be far better than as compared to the lower number of bits. So the summary is that to increase the accuracy, we need more number of levels to completely or accurately recover the digital signal at the receiver side. So there are some digital communication advantages why we are converting analog to digital signal. So there should be some advantages, otherwise no use to convert uh, analog signal into a digital signal. So first one, withstand the channel noise and distortion much better than the analog. So there is a less chances of affecting from the noise and the distortion as compared to the analog, because the reason is that in analog we have a exact value in each shape, right? In each portion we have a value of so if we didn't recover this part, then this it means that this speech or this value will be lost. This doesn't recover, this signal will be lost. So every part has a message, but in case of the digital signal we have a 1 0 or 1 minus 1. So these are the level, right? Minus 1, right? So we transmit 1 here or the 0 bit here, 1 here, 0 bit here. So even if the noise affect this one, but still if it is above this value, for example, if after noise effect this level decreases, but still it's above this line is positive, so we will consider the one is transmitted. So they are very much prone to the noise. So with regenerative repeaters, it is possible to transmit over long distance. We can regenerate after some distance to transmit the digital signal over long distances. Whereas this is not possible to regenerate the analog signals. So digital hardware implementation is flexible. Digital coding provides further error reduction, high fidelity and privacy. Easier to multiplex several digital signals. It is easier to transmit several digital signals together. More efficient in exchanging SNR for bandwidth. Digital signal storage is relatively easy and inexpensive, and reproduction with digital messages is reliable without deterioration. Right? The cost of the digital hardware is cheaper and continue to decrease because of improving the electronic circuitry. So these were the some advantages. Okay, now let's discuss the quantization error model. You know that whenever the signal, for example, xn is quantized to xgn, so there will be some noise in the quantization signal. Why? Because whenever you quantize, for example, there are the levels, right? So if the signal lies in between this, right? So we just here or here, we just map it to the mid value of that level, mid value of the level. So there will be some quantization error because we didn't take the accurate value, exact value, but if any signal lie within this interval, right? So we will map directly to the center value. So there will be some errors. So we called it as a quantization noise. So xn plus egn. So xgn is equal to xn plus egn. So there will be a noise. Where egn is an observation of a stationary random process. So this egn is a stationary random process. And we consider that the noise or the quantization noise is uniformly distributed on the interval minus delta by 2 to delta by 2. Why it's in this way? For example, if you see that this is your quantization level delta, right? Delta V, first delta, and the other is the 2 delta, right? So we whenever there is a mapping, we map into the center point. So from center, let's start again. For example, this one is the level, right? So this is one is the mid value. So whenever we map to the mid value. So the maximum, this width is delta, right? This width is delta. So whenever there is a error, there will be chance that it will be delta by 2 plus side or delta by 2 minus side, right? So it will have a maximum error of delta by 2 because from center to this point, this maximum displacement or the maximum point distance is delta by 2. So there is a maximum chance of distributing this error uniformly within delta by 2 and minus delta by 2. So the uniform distribution of the error will, the PDF of the error will look like this one, delta by 2 to minus delta by 2. And the PDF, like the PDF amplitude is 1 over delta. This should be remembered because this is uniformly distributed. We will use this distribution in the next slide. So you can notice that the PDF, distribution is 1 over delta, right? So EGN noise is uncorrelated, EGN is independent of XN. So it doesn't depend on the uh, input signal, but it's independent and uncorrelated. Okay, let's find the signal to quantization noise ratio, which we called SQNR. So how it represents SQNR in dB, 10 log 10. So this is signal power, this is noise power. But this noise is not noise due to receiver, but this is noise due to quantization error. We called it as a noise, right? So sigma x is the power in xn, the transmitted message. So the power is written as the expectation of x square n. This is expectation, and it is called usually called the variance in communication system, or the probability or random process. You already studied this one, right? So variance, so we can represent the power as a variance, right? So mean of a uh, variance, you can say, right? This is transmitted message, and this is the noise. So noise here is the quantization noise of EGN. So expectation EGN square. Okay, we have usually this signal power given. So to find the sigma square E, we use this equation. How we use? Because in previous slide we have noticed that we have error signal which is uniformly distributed between delta by 2 to minus delta by 2. This is uniform distribution, right? Uniform means their amplitude is same, right? And the amplitude is 1 over delta. So the PDF amplitude is 1 over delta. So let's write minus delta by 2 to delta by 2. E square is the error square, the probability of error into dE. So delta by 2 E square, right? And for the probability of error, right? So by using this 1 over delta, so 1 over delta dE. So it's become, after taking integral, E cube over 3 delta, and putting this delta by 2 minus delta by 2, we will get delta square by 2, 12. So this is the quantization error power, right? So now we can call the noise power. So using this noise in, uh, for example, now first you know that delta is 2 MP over L, using it above. So delta square E in this equation, right? So instead of delta, we will put 2 MP over L. So whole square over 12, we will get equals to MP square over 3L square. So from here we can notice that the noise decreases when the L increases. As I mentioned, whenever the quantization levels increases, so we will get the more accurate signal. So it means that the noise will be less because they are inversely proportional to each other. So thus SQNR for the message signal with the power m square t is signal power over noise power. Just put it here. So we will get the inverse. So m square t, 3l square m square t. So this equation must be remembered because this may be used to calculate some signal to quantization noise ratio in some numericals. Okay, let's move to the non-uniform quantization. So previously we discussed the error is uniformly distributed, and everything, the intervals are at the uniform, like there is a uniformly distributed number of intervals. Like the interval has the constant space between them. Why we introduce non-uniform quantization? The reason is that usually when you speak and I speak, our frequency is in the lower frequency range. For example, you speak and your message generates something like this. So usually it like this, and there are some higher peaks, right, in this way, or lower peaks in that way, right? But usually your frequency is low, right? So if we uniformly distribute the, if we use the uniform quantization, it means the number of levels are, spacing between the number of levels are equal. Then it means that for the less are occurring frequency components, we will allocate the same number of levels. In other way, it will decrease the quantization accuracy. So to improve this one, For lower frequency, we have a more number of levels, right? This one. And for the high frequency, we have a lower number of errors. Look at this. This is high frequency, lower number of errors, levels. So by increasing number of levels, as I mentioned earlier, we have a less quantization noise and more accurate signal. So there are some quantization. This is a way of quantizing the using the non-uniform quantization. So non-uniform quantization reduces the quantization error by reducing the quantization level where the signal is more frequently exists at low amplitude. So we reduce the quantization levels and for the higher frequency, and for low amplitude we have a more number of levels. So there are two laws. These equations are used to find the output of the quantizer, right? This is output of, there is mu law which is usually adopted in North America and Japan, and the A law is in the rest of the world. So these are the equation. I think we don't need to go in more details, but if you want to calculate the outputs using the quantizer, so y will be the output and the mu is the compression parameter. So if more mu, it means that there is a more compression. If low mu, it means that the compression is low. So higher. And m over mp is the normalized value, right? This is your message, and if you divide by the mp, it means you are dividing with the peak value, so it will just not increase by 1. So it will be between 0 to 1. So this graph shows that the m over mp, right? This is your normalized values, and this is your input message, and this is your output message. So for the lower frequency part, we have a higher gap here output, right? It means in the end we have a more number of levels for the lower frequency part, right? So this equation, similarly, there is a which is the compression ratio, and for high number of compression we have a if we have a high, it means that we are using the more number of quantization, right? Non-uniform quantization. If A is, for example, 1, so it means that there is no non-uniform quantization. This is some figures just to show that this, for example, for different value of mu is equal to 0, there is a uniform quantization. Mu is equal to 10, more quantization. Mu is equal to 1000, very high quantization. So there will be different levels. Similarly, this is for mu, and this is similarly for A part. A is equal to 1, we have a no uh, uniform quantization. A is equal to 10, we have a non-uniform quantization, more non-uniform, and highest non-uniform quantization. So if you want to calculate the SNR for the mu law, this is equation already derived, and you need to just remember this one, 3L square log 1 plus mu whole square. So you can directly calculate the SNR for mu law, and mu square should be greater than m square p over message signal, right? And this is non-uniform quantizer. Non-uniform quantizer usually work in this way. First, you will have a compressor which will compress the signal, right? And then you will pass through the compressed signal to the uniform quantizer. In this way, you will get the non-uniform quantized output, right? There is a simple difference, like we have additional blast of the compressor at the transmitter side, and then after doing compression, and the compression depends on mu or A factor, right? We will just pass to the uniform quantizer, and it will give us the non-uniform quantized output, and then PCM channel. And at the receiver side, because at the transmitter side we did the compression, at the receiver side we did the expansion, right? So there is an expansion. So this is the curve. This is your relative signal power, and this is SNR. So for mu is equal to 0, and we have a non-uniform quantization, and here we have a non-uniform quantization. Mu is equal to 255. This is just to show that how the power versus SNR. What is the relationship between the power versus SNR in case of non-uniform and uniform quantization. Okay, there is another concept of transmission bandwidth we already studied, that bandwidth should be uh, we mentioned that the information can be transmitted successfully with without in the noiseless channel without any distortion if the bandwidth is 2B, right? 2B information is transmitted if the bandwidth is B, right? Without any. So each quantized sample is thus encoded into n bits because you know that we need to, whenever we quantize, we need to encode into the number of bits which can be n, 2, which can be 2, 3, 4, so on. Because signal empty is band limited to B hertz, so a minimum 2B samples per second, as I mentioned, where we require a total 2 NB bits per second, that is 2 NB pieces of information per second. If we consider that a unit bandwidth of 1 hertz then can transmit a maximum of 2 pieces of information per second, and we require a minimum channel bandwidth. This is channel bandwidth. This is your signal bandwidth B, and this is your the channel bandwidth. So channel bandwidth is n times B hertz, right? So n is the number of bits and B is the frequency. So this is the theoretical minimum transmission bandwidth required to transmit the PCM signal. So without this is the minimum. If you have a NB hertz bandwidth available, it means if you are transmitting 2 bits per symbol, 3 bits per in quantization symbol, then you need 2 B hertz and 3, then 3B hertz. This should be the channel bandwidth, minimum required bandwidth. If you have a less than this, then there will be error. Okay, this is an example to clearly show that what is the role of the transmission bandwidth. For example, if you have a signal empty band limited to 3 kilohertz, so B here is 3 kilohertz, which is sampled at the rate 3313. So 3313% higher than the Nyquist rate. So it means that its rate is 33.3% higher than the original Nyquist rate. So original Nyquist rate is 2B. So we need to add this 33% of the bandwidth of original 33.3% of the bandwidth of the original signal. So the maximum acceptable error in the sample amplitude, the maximum quantization error is 0.5% of the peak amplitude. So 0.5% of the peak amplitude is the allowed error, right? MP, right? The quantized samples are binary coded, so we need to find the bandwidth, minimum bandwidth of the channel required to transmit the encoded binary signal. This is one part. And if we have a 24 such signal that are time multiplex, determine the minimum transmission bandwidth required to transmit the multiplex signal. So there are two parts. One is we need to find the minimum bandwidth when there is a one signal, and when there are 24 such signals, then with that a time multiplex, then what will be the minimum transmission bandwidth required? Okay, let's start. So you know that the Nyquist sampling rate is twice of the bandwidth. So here the bandwidth of the measured signal is 3 kilohertz. So using that here, so 3000 hertz it means, so 6000 hertz is your bandwidth samples per second. Now you need, but they mentioned that they sampled at 33%, 3.33 or 13% means 33.3% higher than the Nyquist rate. So it means that 33% point 3 of 6000 is 2000. So the total sampling rate is 6000 plus 2000. So it means they are sampling at the 8000 hertz. And the quantization step is delta V, and the maximum quantization error is delta V over 2Q, as we already studied before. Okay, so therefore from equation 6.31 in the book, so you know that we have the equation 2mp over L is equal to delta. So using this equation, so we have a delta V over 2, right, mp over L, right. So as they both are equal, because we don't have the value given of delta V, so we will just equate this to mp over L. So we have the maximum allowed error 0.5% of the MP. So 0.5% means 0.5 over 100 of the MP. So MP over L is equal to 0.5 over 100 MP. So just we need to take out the number of levels as we want to calculate the L here. Others are known. So MP will be cancelled out. So L equals to 200. So now 200 is because there is a for binary coding, L must be a power of 2. It must be a power of 2. Hence, the next higher value of L, that is power of 2, is 256. So we just approximate it to the 256 because we need in the power of 2. So the number of bits required will be n is equal to log 2 256 into log 2 L. It means so 8 bits per sample. So it means that we are transmitting for each sample, we are transmitting 8 bits. So we require to transmit a total of number of bits. How much? 8 into 8000 samples per second. So total bits, because there are 8000 samples and we need 8 bits per sample. So total bits per second will be 64,000 bits per second. But we need to find, this is the total capacity or the total bits we need to transmit. But how much channel bandwidth is required? As we know that we can transmit up to 2 bits per second per hertz of a bandwidth. So minimum transmitted bandwidth is C over 2 is 32 kilohertz. It's the half of the number of bits. Because for each unit bandwidth we can transmit 2 bits. So this is the one part. So there is a channel bandwidth. If we have a one signal, it's 32 kilohertz. So if we time multiplex, so we have a 24 into 64,000 because there are 24 channels and 64,000 per one channel bits per second. So we have a 1.536 megabits per second, which requires 1.536 over 2.768 megahertz transmission bandwidth. So it means that to transmit 24 channels such signals simultaneously using a time multiplexing, we must have a 0.768 megahertz bandwidth. Okay, let's go in detail. PCM based TDM system. This is a practical system usually adopted in the telephone lines. So PCM is widely used in the transmission of speech signal in fixed line telephone system. For example, in our case is a PTCL, so we use PCM. In this lecture, we shall briefly explore an example of PCM, the T1 carrier system. There are two systems. First one is the T1 system, which was developed at the Bell Labs and is still in use today in the US and Japan. And the similar scheme like T1, we have T1, which is used in Europe and Pakistan, in the rest of the world as well. These schemes are used to multiplex the speech from multiple subscribers and transmit them to their destination over a common time shared channel, and it is named as time division multiplexing. So this is one kind of a multiplexing scheme where we can transmit the number of signals over a same channel. How it works? Let's move on. As you know that the sampling rate used for voice is 8000 samples per second. So this is the rate. So to find the time, so time should be inverse of the rate, so, right? Time is 1 over fs. So sampling time, what will be the sampling interval or the sampling time? 1 over 8000, 125 microseconds. It means that for a first sample, when for a one message signal, right? This means that the time between two consecutive samples from the same source. For example, I am speaking, so my first sample will arrive, digital sample will arrive at 125 microsecond at 0 second, for example. Then next will be apart 125 microsecond, and the third sample will be 125 microsecond again. So this 125 microsecond gap is used to transmit the other source data. This is called time division multiplexing. For example, this is your data, my data. I am transmitting here. So after 125 microsecond, I have another data. This part is free. Here we can transmit other source data in this part, right? Because my sample will be after 125 microsecond. So TDM system exploit this fact and utilize this interval to sample signals from other subscribers, right? In T1 system, the signal from 24 subscriber is sampled in 125 microseconds. So within this gap, we can transmit 24 other subscribers as well. The samples are quantized and then converted to a bit stream for a transmission over the channel. This is one picture showing that you have this is my first sample and my second sample will arrive after 125 microseconds. So this is the free time where we can allow the transmission of the other subscriber. For example, this is sample 1 and sample 1 of channel 1, it means user 1, and sample 2 of sample 1 of a user 2, right? Different color. Similarly, user 3, sample 1. So again, here is a, uh, it means that there are 24 subscribers which are transmitting in within 125 microsecond. And afterwards, 125 microsecond passed, time for sample 2. Now there will be another sample from this user. Look at this. So sample 2, user 1. It will continue for other signals as well, other subscribers as well. So every sample, as I mentioned, is represented by one of the 256 quantization levels that is closest to it. This corresponds to 8 bits. It means that for each sample we are transmitting 8 bits to transmit one sample. So this is one sample. So if you clearly notice that there are 8 number of bits for one sample. 1, 2, 3, 4, 5, 6, 7, 8. So these are 8 bits we are transmitting for each sample. So there are 24 such samples. So in TDM, so each frame we call this frame. So 24 subscriber, 24 into 8 bits each. So we have a 192 data bits and takes 125 microseconds. So at the receiver, but there is a problem. How we know that the other sample is started? So to notice this, our other frame is started. We uh, necessary to know where the frame starts in order to separate information bits. We add an additional bit which is called a framing bit at the beginning of each frame. So there will be a total number of bits 193 instead of 192. For each bit frame there will be additional one bit which will be transmitted in parallel. So look at this. This is framing bit and this is channel 1, and then this is channel 2, this is channel 24. So 24 channels, and for each there will be a one framing bit at the start of each frame, and then after 24 channels there will be again one framing bit here, right? And this one will be the, it will continue. Look at this: frame 1, frame 2, frame 3, frame 9, each are of 125 microsecond in time domain. So thank you for listening, and for question answer there will be a separate session. So this is all from this course, and hopefully you have learned some good ideas from these videos. Thank you for listening.